Welcome to this MOOCs online course on fluidization engineering. So, today's lecture will be on solid mixing and segregation in liquid solid fluidized bed. We think we have discussed about the solid mixing and segregation in gas solid fluidized bed in previous lectures, and there we have actually discussed about the basics of segregation mechanism, even how the solids will be mixing there only for two phase flow of gas and solid system. But what about the solid mixing and segregation in a liquid solid or gas liquid solid systems in the fluidized bed? So, this lecture will be continued with that continuation of the solid mixing and segregation mechanism for this liquid and solid system. I think we have already discussed about what is the mixing and segregation, what is the definition for mixing and segregation there, what is the mixing index, what is the segregation index, and how this mixing index and segregation index are correlated. Even what are the different models for that mixing and segregation for this gas and solid systems. Here same type of definition of course will be there, but in this case you will see that maybe some different phenomena will be seen there for liquid if instead of gas is used in the fluidized bed. In that case you will see that sometimes the liquid properties will affect the segregation and mixing inside the bed, because that gas has lower viscosity, whereas if you use the liquid, then of course there will be some difference in phenomena because of this fluid properties. In this case of course, there is the same criteria for that, whether these solids will be considered as complete mixing, or the solids will mix partially, or it will segregate partially or not. Even if there is a segregation, whether it will be complete segregation or partial segregation, and also what should be the mixing and how it can be measured, this mixing criteria for the solids in the liquid phase, and how that mixing and segregation depends on. I think we have already discussed about that this mixing or segregation that depends on the relative size of the particles and shapes, and also the density of the particles. But you will see that relative density in case of gas and solids, there will be very that effective in that case. In that case you will see that mainly gas density is very low compared to the solid density, whereas in case of liquid, that if you are using water or some other liquid, of course its density will be more than 1000 there if it is heavier liquid than water also. And in that case, that effective density of that is density difference of that solid particle and the liquid will be of course lower than that density difference of that gas solid system there. So, based on that also, that density, effective density difference, that mixing and segregation will be affected. So, in this case when two or more species of particles that are in fluidized condition, then you will see that the solid or liquid mixing will be maybe completely or maybe partially, or maybe segregation in a complete manner, that depends on the relative size, shapes and densities. And the segregation of the solids in the liquid solid fluidization, that depends on of course pressure gradient. You will see that gas solid system, the pressure gradient will be something lower than that, the pressure gradients will be more higher in the liquid solid systems, because here frictional resistance to the wall will be more in case of liquid there. So, segregation of the particles in the liquid solid fluidized systems, that how or what will be the extent of pressure gradient there, that depends. And of course, you will see that constant axial pressure gradient throughout the bed, that denotes that perfect mixing of the particles, and whereas the variation of this gradient signifies there will be a segregation. And the larger the variation of pressure drop or pressure gradient, larger the degree of segregation will be in the fluidized bed in case of liquid solid system. Now, how this segregated particles can be distributed, and what should be the segregated particle size distribution there in the fluidized bed, and how it can be represented. Generally, a cumulative fraction of the particles that larger than particular size like dP, in that case all of which are presumed to be located below level Z, then it can be expressed as that by this equation here, one given in a slide here C. This will be equal to mz by m. Here mz is defined in such way that is related to the pressure gradient here, small mz. So, this mz by capital M, it is this is similarly simply that the ratio of the pressure gradient up to a certain distance and based on the total distance, of course. So, first you have to calculate what should be the pressure gradient at a certain height, if you are considering of that fluidized bed, then up to that distance you have to calculate what should be the pressure gradient, and this pressure gradient of course will be the frictional pressure gradient. And also you have to calculate what should be the frictional gradient, frictional pressure gradient for the whole fluidized medium. So, in that case what should be the ratio, that will be represented by this mz by m. So, this is actually this pressure gradient, frictional pressure gradient, that depends on that particle size distribution, of course, there. So, this can be represented at that if there is up to z location 0 to z integrated, then 1 minus f d into d z there. So, here 1 minus f d is the particle size distribution function there. So, it will be 1 minus f d into d z, and small m z that can be represented, that is actually defined by this here m z is equal to rho p into a divided by gravitational acceleration into rho p minus rho here. This is the relative density, that is particle density to the fluid density there, and integration of this here pressure, frictional pressure gradient. So, after that you will be able to calculate what should be the m z there after knowing all that in pressure gradient there. And epsilon is one important factor here. This epsilon is nothing but that this will be the porosity, or you can say the void fraction of the liquid inside the bed except solids there, and this directly it will be related to the frictional pressure drop. You will see that this can be calculated from the frictional pressure drop here by this 1 minus d f by d z by g into the relative density there, and this depends on the particle size distribution inside the bed. And capital M should be represented by this again with the pressure gradient based on the total length of the fluidized bed there. So, the mass m z of the particles between the distributor and the height z m can be calculated, and from which this capital M actually can be represented by the total mass of the solids inside the bed, that can be obtained from that pressure gradient. And again then if you actually know the pressure gradient, then what should be the local composition of the segregated solids inside the bed. Now, you will see that for the particular case of a binary solid mixture in the fluidized bed, you will see that you have to have some local mean particle diameter that will allows one to determine the local composition of the solids. Now, the local mean diameter to be expressed as a function of bed level in the transition zone between the fully segregated large particles at the bottom and the fully segregated small particles at the top. That already we have discussed in the gas solid fluidization system, that there will be two portions of that fluidized bed, one is bottom and the top, and the smaller particles will be segregated to the top, and the bottom one the coarser particles will be deposited as a segregated solids there. So, in these slides also you will see that from the bottom to top how the solid particles will be segregated. You will see that in figure A, here there will be complete segregation. It is obviously actually that the smaller particles, see how it will be segregated from the coarser particles here, and the smaller particles are separated at the top region of this fluidized bed, whereas these coarser particles will be segregated or deposited in the lower part of this fluidized bed. Whereas, if they are perfect mixing, you will see that smaller and coarser particles will be distributed throughout the column, and there will be no segregation. In that case, you can say that smaller and coarser particles there may not be separated in the bottom and topper portion, and maybe smaller particles will be also at the bottom, and coarser particles also will be at the top portion. So, there will be a segregation that depends on the mixing characteristics. Now, if higher mixing or higher flow rate is controlled inside the bed, then you will not be able to get the segregation at 100%, but whereas at a certain gas flow rate, you will see that there will be complete mixing, by which you can say that small and coarser particles will be distributed throughout the column, and then concentration of these smaller particles and the coarser particles will be actually equally distributed in such a way that you have to maintain certain gas flow rate and pressure distribution there. And based on this perfect mixing, you will see that the pressure gradient will not be changing along this height of the fluidized bed, whereas for complete segregation, you will see that at the bottom part there will be that means dense region of the coarser particles will show you the higher pressure drop, whereas at the top portion finer particles, that means their porosity will be more higher there. In that case, that friction or pressure drop will be less compared to the perfect mixing there. Whereas, this partial segregation, you will see that some smaller particles, very less amount of smaller particles will be actually residing at the bottom of this fluidized bed, whereas maximum portion of the coarser particles will be residing on the bottom side, and very small amount of coarser particles will be depositing at the top portion. So, they are partial segregation that you see that maybe some concentration of the solid particle very dilute way, you can say that it will be mixed in the lower part to the coarser particles, whereas partial segregation, in that case you will see in figure C, there may be increasing in such way that if you are increasing flow rate and also energy distribution is so high, and also if you change the viscosity of the liquid or higher viscous liquid, if you are using or lower viscous liquid using, then that case you will see that there may be a again the mixing, some extent mixing of the coarser and finer particles will be on the fluidized bed, and then the segregation efficiency or partial segregation will be there some extent there relative to the figure C. So, in this case you will see that very interesting that whenever this partial or complete segregation will be there inside the bed, then you will see that the local mean diameter, that is that will be changed across this column, and it can be expressed as a function of the bed level in the transition zone between the fully segregated large particles at the bottom and the fully segregated small particles at the top. So, in that case of course, you have to know how this local composition of these solids will be changing based on the flow rate of the fluidized bed, and what extent of this segregation can be obtained by this phenomena. And you will see there of course, to determine the local mean diameter using this axial voidage profile. Of course, during that complete or partial segregation, the local voidage of the liquid there will be change. At the top maybe higher voidage will be there, whereas at the bottom maybe lower voidage will be there. So, based on this axial voidage profile, D. Felice et al. 1987, they have suggested one actually empirical equations for calculating this what is that local mean axial voidage by knowing that local mean diameter by this segregation phenomena. So, as per their model, they have given this equation 2 here, and it is expressed as in terms of Archimedes number and the Reynolds number. So, Archimedes into epsilon to the power 4.8, that should be is equal to 17.3 into R e to the power alpha, and plus 0.336 R e to the power 2. Here R e means Reynolds number and A r means Archimedes number. So, this Archimedes number is defined as here particle diameter cube into effective density into fluid density to gravitational acceleration by viscosity square, where alpha is one important empirical constants that can be obtained from the experimental data, and this is correlated with that porosity again. So, alpha should be is equal to 2.55 minus 2.1 into 10 h into 20 into epsilon minus 8 to the power 0.33 whole cube. So, in this case very interesting that this correlation coefficient here will be some extent that depends on the experimental data, how this experimental data are fitting with this empirical equations there. Anyway, they have suggested, I think after comparing with different models, and they have given this finalized model there. And this constants here alpha, that depends on this again this porosity. So, once you substitute this alpha here, then porosity equation will be represented by this equation 2, and solving this nonlinear equation of porosity by changing the gas velocity changing the fluid density and the liquid density there, and with other variables, then you will be able to calculate what should be the porosity at a different level. And local composition of the segregated solids also, there of course, it will be varying along with this axis of this fluidized bed. So, degree of segregation or mixing irrespective of that, the overall bed expands as it is simply the sum of the number of individual species is acting independently of the other. So, Epstein et al. 1981. So, irrespective of this degree of segregation or mixing, the overall bed expands, how much bed expands based on the voidage inside the bed, that depends on the number of individual species, and then each species will be acting independently of the other. So that this 1 minus epsilon, that means here the what should be the volume of the solids inside the bed, that depends on this local or overall volumetric concentration in the liquid of that particle species I. So, if particle species concentration of I is C I, then it will be C I by C T and divided by 1 minus epsilon, and if you are summing up all these here for the n number of species inside the bed for different particles, and then you will be able to calculate what should be the overall bed expansion based on this concentration of the liquid or particle species I there. And epsilon I is the voidage when species I is the fluidized alone at the same superficial liquid velocity as the mixer, and C I by C T, that is given in equation number 3 here, is the volume fraction of the fluid free solids, which is for the species I. Now, using the measured variation of this frictional pressure gradient with height of the column, the procedure of this method procedure of that given by that D. Felice et al. 1987 can also be applied here by changing the composition with bed level up to spherical particle species, and that species will have of course the different in both diameter and density. So, if the spherical particle species will differ and their density also they differ, then you can calculate that the density of that particles by means of an additional equation of the volume average density there. So, this average density of that particle there inside the bed, that will be equal to C 1 rho P 1 plus C 2 rho P 2 rho P 2 by C 1 plus C 2 there. So, here you can calculate this average volume average density here as like this by equation 4. Now, what will be the phenomena involved in particle mixing and segregation there? In the case of a size difference alone, the larger particles will always separate to some degree below the smaller under this following conditions there. So, their size difference one condition, and the bulk circulation or hydrodynamic instability. So, the larger particle separate to some degree below the smaller unless the size difference is small enough. And also it is seen that complicating factors such as bulk circulation also will govern the degree of segregation based on the size difference there. Also, there will be of course the hydrodynamic instability, maybe flow pattern inside the bed will change, and because of which that the segregation pattern and also the mixing will also be changed because of that hydrodynamic instability. And hydrodynamic instability are large enough to mix the two particle species completely there in the bed. Now, if there is a shape difference, what will happen? Now, if the shape difference of this particle, sometimes the different shape of the particles will be there inside the bed. Now, the species with the larger magnitude of the product, like here phi dp, phi is the sphericity and dp is the particle diameter, will generally segregate below. And if there is a particle density difference, you will see then the difference is in the same direction as that of phi dp in the previous case, and the segregation will be accentuated. And phenomena that involved in particle mixing and segregation, that also depends on that density difference of that fluid particle, and also the void is inside the bed. The density difference is in the opposite direction. Then depending on the magnitude of this difference, the segregation may be attenuated throughout the entire voidage range as the liquid velocity is increased. Now, it may sometimes happen in reverse direction over the entire voidage range, or it may be reversed at the lower voidage and attenuated at the higher, that depends on the fluid density. The last situation is that that interesting bed inversion phenomena is that. So, sometimes that bed fluids will be inversing their phenomena of that mechanism of that what is that fluid particle segregation and solid particle segregation inside that. Totally that depends on that diameter and also the flow rate and also the fluid properties of the system. Now, how this segregation phenomena for material having two different sizes can be obtained and can be actually quantified then. Let us consider the fluidization that occurs with that spheres of density rho p and the diameters dl for large particles and the diameter ds for the small particles, and having a spherical liquid velocity u there between umf L and u 0 s. u 0 is called terminal settling velocity for the particle of smaller size. And in the absence of smaller particles, so the fluidized bed suspension density to be actually calculated based on this equation 5 here. Now, here in this case this the fluidized bed suspension density will be is equal to rho p, that means density of the particles into 1 minus epsilon L. 1 minus epsilon L is nothing but the volume fraction of the smaller particles there, and then density of the liquid into epsilon L is the what is that porosity of this only liquid volume fraction there. And in the absence of larger particles, the suspension density will be given as rho p into 1 minus epsilon s into rho into epsilon s here. So, epsilon L and epsilon s is the volume fraction of the larger particles and smaller particles there in the bed. And if you know this volume fraction of the smaller and larger particles there, then what should be the suspension density based on that larger particles and smaller particles there. So, rho p is the particle density, rho is the liquid density, epsilon s is the volume fraction of smaller particles, epsilon L is the volume fraction of larger particles, by which you will be able to calculate what will be the fluidized bed suspension density by this equation number 5 and 6 here is shown in slides. Now, if you subtract these two equations of this 5 and 6, then you can simplify it as by this equation number 7, and defining the dimensionless density ratio and defining by this equation number 8, then you can represent this equation here as gamma is equal to epsilon s minus epsilon s L, where epsilon s and epsilon L are the voidage displayed by the respective monocomponent beds when they are each separately fluidized by the same liquid at the same spherical velocity u as the binary particle bed mixture. As per research on Jackie 1954, they have developed one correlations for this gamma which is applied for the monocomponent beds here. So, they have given this here gamma is equal to epsilon L into dl by ds to the power 3 minus m by mn, where this m and mn are the parameters that depends on the other properties of the fluid. So, the index n here given by this equation 10 or 11 here, this n can be calculated by this equation number 12, this 4.8 minus n by n minus 2.4, that will be equal to 0.043 into Archimedes number to the power 0.57. Now, this m and n, so n can be calculated from this equation 12, whereas m also it depends on the different fluid actually condition, whereas this high velocity fluid or low velocity fluid, that means here the regime of this condition, sometimes whether for laminar regime, then it will be Stokes regime, and sometimes Newtonian regime may be more than Stokes regime there. So, that varies based on that fluid flow condition there. Now, this exponent m generally varies from 1 in the Stokes regime, and it will be 2 to 2 in the Newton regime. And according to that 3 minus m by m n, this coefficient here in this equation number 10 and 11, it is seen as per their experimental data, and they have stated that this coefficient, this 3 minus m by m n will be varying from 0.43 to 0.22 as one moves from Stokes regime to the Newton regime. So, by this equation number 10 and 11, you will be able to calculate what should be the porosity of the fluidized bed for the smaller particles and larger particles by knowing this equation number 11 and 10. And of course, along with this index n for this by this equation number 12. As if the inertial effects and the turbulence increases, you will see that the degree of segregation decreases, that given by this Epstein and Pruden 1999 in their article. And even without complicating effects such as bulk circulation and hydrodynamic instability, you will see that inertia effects and turbulence also will change, and because of which this segregation and its degree will be affected by that phenomenon. Now, some qualitative measurement of the degree of segregation is given by Epstein and Pruden there, and the value of gamma they reported that may be a function as a crude qualitative measure of the degree of particle segregation as follows here. Now, they have given this some range of that gamma value. If gamma is less than 0.015, then you it will be noted that there will be a little segregation and good perfect mixing as shown in figure B. Whereas, this gamma value, if it is within the range of 0.015 to 0.045, and as per figure here in their D, then you will see that partial segregation with no interface between layers will happen there. Whereas, 0.05 and up to 0.1, it is seen that this gamma value will be there, then segregation with fuzzy interface and some intermixing as shown in figure C there in the slides. And if suppose gamma value is greater than 0.1, it is seen that there will be a clear cut segregation with sharp interface and little intermixing there as shown in figure A in the slides here. So, based on this gamma value, qualitatively at least you can say how much segregation or what is the degree or intensity of the segregation in the bed that you can calculate, that you can of course identify and interpret on that. And another important that axial dispersion coefficient for this particle segregation when it will be there, then how this dispersion of the particles will be inside the bed. Kennedy and Breton 1966, they have actually interpret this phenomena that if binary particle stratification is in the fluidized bed, then based on this stratification axial dispersion according to the Fick's law of diffusion in competition with the segregation can be explained. Now, as per their model that if you consider a semi-vast liquid fluidization that results in partial segregation of the type that is represented in figure C and D here in this slides, then you will see that at any bed level within the partially mixed region, the volumetric particle mixing flux for the species I that must be equal the particle segregation flux for that species. So, in that case equation 3 will be useful to actually interpret that axial dispersion there inside the bed. Now, they have actually concluded in this way that as per their as per Fick's law of diffusion, they have given this equation of 13 by that the density or you can say that concentration of that species with respect to z at a steady state condition will be actually depending on the what is that particles flow rate there. That means, or you can say that segregation velocity of the species through a swarm of species j in the mixture. So, in that case this proportionality constant maybe will be expressed by this axial dispersion coefficient. So, based on their model this equation 30 can be explained here. So, d I into d C I by d z, that will be equal to C I into u p I there. So, C I is the proportionality constant and d I is called the axial dispersion coefficient of the species I, and u p here is the segregation or you can say classification velocity of that species in the bed. Now, according to their model that segregation velocity u p I can be expressed by the difference between the local interstitial velocity of the fluid in the bed and the interstitial velocity can be expressed by that here it will be equal to u by epsilon by u I by epsilon here. So, u is the gas velocity and epsilon is the porosity of the gas. So, u by epsilon this is called but axial velocity of the gas, whereas this u I by epsilon, that means here u I is called the species segregation velocity and epsilon is that what is that void is inside the bed. So, based on this you can say that what should be the slip velocity of that segregation velocity or relative velocity of the segregation velocity you can calculate it in terms of this axial or interstitial velocity. So, for a monocomponent system or for the fully segregated region of either a partially or fully segregated bed, then you can say that the u p I value should be equal to 0 and whereas this u will be equals to u I, that means gas velocity will be equal to that individual species velocity. In that case you will see that particles in the segregated regions that will be involved in the bed. So, in this case you will be actually expressing how that slip velocity will change that extent of segregation or degree of segregation, whether it will be that partially or fully segregated bed are there or not. So, you have to first you have to calculate what should be the that means local or you can say that slip velocity of that local velocity of that segregated particle there. And substitution of this u I value here you just substitute it in equation number 13 there, then you will be having this equation which is expressed by equation 15 there. And in this case for the large particles both sides of this equation are negative, whereas for the small particles both may be positive. So, d I can be determined from the measured axial concentration profiles of this C L and C S and or by this epsilon is equal to 1 minus C L minus C S there. So, based on which so equation 15 can be expressed and by which you will be able to calculate this axial dispersion coefficient this d I just by plotting this gradient of this concentration with this u or epsilon there inside the bed. Al Debouni and Garside 1979 for partially segregated beds with no transition zone, they have developed another equation by integration of equation like this. Here it is expressed in equation number 16, and based on this equation 16 you can also be able to calculate what should be the axial dispersion coefficient in the bed for that particular species. And from the best straight line through this moderately scattered plot of this left hand side of the above equation versus this log of C I by C 0, if you plot, then you will be able to calculate this d I value. And this slope of which equals to that 2.303 into d I for this equation number 16, and then from which you will be calculate what will be the d I. Now, Juma and Richardson 1983, they have also given another equations to calculate this that means their segregation velocity, that is along the axis of the fluidized bed, and they have given this equation of this here u p I is equal to a I plus b I into z. This a I and b I are the parameters which is to be experimentally determined. Here I means L and S, that means large and smaller particles. So, here for the larger particles, so u p L that will be equal to a L plus b L into z, and also for smaller particles u p S is equal to a S plus b S into z. Now, if you are able to find out experimentally how this u p for large particles and then for smaller particles these velocities are changing along with that z, then you can mathematically express that segregation velocity for this large and smaller particles by this equation number 17. And from the experimental data you will be able to find out what should be the parameter of this a I and b I for this equation 17. Once you know these parameters a I and b I, then automatically you can say that what should be the predicted value of this u p I for any operating conditions there. Once you know this predicted value of that means segregation velocity for this large and smaller particles by equation 17, and if you substitute there, of course, you will be able to find out what should be the axial dispersion of the this larger and smaller particles inside the bed for this binary mixture. And equation 16 can then be integrated by knowing this parameter a L B L or A S B S as then, and substitute here you will get this type of equation, and from which individually for individual component of this larger and smaller particles this dispersion coefficient you will be able to calculate. Here it is important that where the void is at z is equal to 0, the bottom part of the transition zone and below is the epsilon L, and the void is at that is at the top of the transition zone and above is epsilon S. Now, d L and d S best fitted to the experimental measurements according to equations 18 and 19, then you can obtain obtain the value and adjust it to best match the profile of that C L and C S, that will be equal to 1 minus epsilon versus length of the Z, length of the fluidized bed there. So, from this equation 18 and 19 you will be able to calculate what should be the dispersion phenomena, dispersion extent of dispersion of this large and smaller particles, and along that Z how it will be changing also. Now, the u p I varies linearly with C I from 0 in a monocomponent bed of that I particles, in which that epsilon will be equal to epsilon I, and C I will be equal to 1 minus epsilon I to u p I 0 in a monocomponent bed of Z particles, in which you can say that epsilon is equal to epsilon j and C I will be equals to 0. So, that that UPI should be is equal to UPI 0 into 1 minus Ci by 1 minus epsilon I. So, this relation has been given by actually the Bhendir, Meyer et al. 1984 and D. Felice et al. 1987. Also Aship and Peterson, they have also 1993, they have also studied this how that is segregated velocity for the large and smaller particles will change with its concentration, and they have also suggested this the same type of relationship with the concentration, and which is expressed in equation number 20. Now, substituting this equation number 20 into again in equation 13, just by taking I is equal to L for larger particles and the upward direction as positive, then you will get this equation number 21. And after simplification of this 21, then you can express this here by equation number 20, and if you integrate this equation number 20, then you can get this Axial, that means here mass fraction of this large particles there in terms of that concentration, then at Z is equal to Z L, then you can express this equation to predict this what will be the mass concentration of these particles there along with the axis of the bed. Now, from equation number 23, it follows also that Axial should be is equal to this here, this it will be related to this Peclic number here. This Peclic number is denoted by that axial dispersion coefficient of these large particles there. So, if you know that axial dispersion coefficient of the large particles, then you will be able to calculate what should be the mass fraction of the larger particles there in the bed. Along also, if you know that the Z, that is here by equation that Z minus Z L, that will be Z minus Z L by L. Similarly, it can be shown for smaller particles also, this excess will be equal to this by knowing that dispersion coefficient for the smaller particles, which is expressed by this Peclic number here in this equation number 25, whereas this Peclic number of the small particles will be defined by this here L here, this length of the bed into UPH0 means here the separation velocity for these smaller particles divided by this dispersion coefficient of the smaller particles there. Now, the Felice et al. 1987, they have also correlated with this CS and CL by their what is that porosity of the smaller and larger particles by equation number 26. And if you substitute this CS from this equation number 26, then Xs can be calculated in terms of XL there by this equation number 27. So, this equation 27 actually is coming after simplification by substituting this concentration profile for the smaller particles in terms of larger particles. Now, comparing this equation number 25 and 27, you can simply say that Peclic number of the large particles will be is equal to Peclic number of smaller particles in magnitude, but opposite in direction, because the flow of the smaller and larger particles will be in the opposite in direction there. And of course, that what will be the length of occupation of the larger particles inside the bed, and what will be the occupation of the smaller particles inside the bed, and then that should be equal to almost the same. So, at the middle of this fluidized bed, it is it will be seen that there will be a demarcation of this larger particle and smaller particles. If the Peclic number of these smaller particles and larger particles are same, or you can say that dispersion coefficient of the larger particle and smaller particles are same in the bed. And if in this condition, this is happening only then, only when there will be the that is concentration of the smaller particles will be based on this correlation with the larger particle concentration. Now, the Felice et al. 1987, they have reported that this axial dispersion coefficient for this larger or smaller particles generally varies from 0.24 to 515 centimeter square per second from the literature data, and they are also experimental data. For a large number of binary systems of spheres from the literature covering the range of Reynolds number, that is 0.5 to 1000 and porosity of 0.50 to 0.95, Ashif and Peterson 1993, they have suggested these correlations for this dispersion coefficient of these larger or smaller particles inside the bed for their segregation phenomena. So, this will be expressed by this equation, and which is a function of this gas velocity, density of the liquid, porosity of the fluid, and also what is that here the particle diameter, and of course, the minimum velocity for the fluidization condition, in which you will see that UMF is presumably applies to the larger particles. So, that the both are fully fluidized there in that case. So, here important is that this UMF should be considered based on the larger fluidized larger particles there. So, once you substitute this UMF U and U 0 there, and you will be able to calculate what should be the diameter what should be the dispersion coefficient of the particular large particles or smaller particles inside the bed. Now, some case let us see here for binary mixture of equal size particles there. It is obvious that multi-size particles of fixed density is far more common in industrial situation than that a particle of uniform size having different densities. Of course, in different applications you will not be having the same size of particles there. For mixture of particles, of course, they are in that way that whenever you are making grinding, and then you will not be having the same size particles there. And but for the same size of different densities, what should be the segregation criteria also, that should be known there. Consider the spheres of diameter dp and density rho ph for higher density and rho pl for lower density, where this rho ph is greater than rho pl, fluidized by liquid having the spherical velocity superficial velocity of the liquid u between UMF h and the UO L here. Then the degree of segregation by that particle density can be expressed by this equation number 29 given here. In this case, this rho b h for larger particles here will be expressed by this equation here, and then rho b L to be expressed by this equation. And equation 30 is denoted for that porosity for that higher density particles there in terms of that lower density particles there inside the bed. And this n, of course, that we have already shown that how n should be calculated this here, and m and n should be what would be the value m n equals to the 4.8 both in the Stokes and Newtonian regime. So, by this equation 29 to 31 you will be able to calculate the degree of segregation by particle density there. Here non-dimensionalized bulk density difference of the two particle spaces in two types of binaries in this table are shown, how this epsilon s and epsilon L and also the gamma are changing for different density and for different particle size there. So, from this table you will be able to calculate, or you can get the different values for this porosity and what is that gamma value. And also another important that if you are using that binary mixture of particles that differing in size and density, and there will be bed inversion there. So, consider a binary mixture of spheres of diameter DIL and DHS and densities epsilon PIL and epsilon PS H respectively, and then for the larger or less dense particles along to the liquid fluidization, it can be represented that this rho b I L will be equal to that rho p I L into 1 minus epsilon plus rho epsilon there. So, similarly for the smaller denser particles also you can expressed by this equation, and the reduced bulk density to be explained by this equation. Then it will provide the indication of the degree of segregation in accordance to this equation here shown in the slides. Now, according to Jean and Fan 1986, this segregation velocity of the species S s with respect to the species I L, that will be given by this equation here. Now, the inversion condition you will get if you just derivative and considering it will be equals to 0, then d u p h s by d u is equal to 0. So, at this condition there will be inversion. So, at the inversion velocity what will happen, the entire bed attains a uniform composition that will be equal to that of the overall solids composition, that means x I L, that should be equal to 0.4 and a bulk density equals to 0 rho b b there. So, more informations you can get from other references that is here given, and so by this lecture what we conclude that we are able to know then in liquid medium how actually the segregation and extent of segregation mixing are happening, and how the dispersion coefficient of that larger particle and smaller particles based on the segregation velocity, how this dispersion coefficient is changing, and also how different sizes and densities of that particles in this liquid medium will affect that segregation velocity and consequently the dispersion coefficient inside the bed. And also what should be the inversion case will happen if you know the inversion segregation velocity for that individual particles with different densities, then how it will be this inversion and what is that inversion condition. It is very important that when that larger particles and smaller particles will be mixed in such a way that at a certain velocity you will see that entire bed will attain a uniform composition that will be equal to that overall solid composition. So, based on which you will be able to analyze that fluidized bed and the fluid mixing inside the bed based on this segregation phenomena. So, I think the lecture may be very useful for that analyzing the axial dispersion of the solid particles inside the bed in liquid solid system. Also same concept also you can use for if there is gas is applied in that gas liquid solid fluidized bed there. So, only thing is that you have to consider the density of the fluid only for that the mixture of gas and liquid as one fluid there. So, and other properties will be almost same for the solid particles there, and then how this axial dispersion coefficient of that solids in the mixture of gas liquid there will be happening, and then you will be able to calculate based on this concept. So, that will be caused that will be called that dispersion phenomena 3 phase fluidized bed system. So, and I think this lecture will be helpful for analyzing also for gas liquid solid system, and more reference are given here to get more information about this. Okay. And in next lecture we will be considering about that gas dispersion and interchange there in the fluidized bed there. So, thank you for your attention.